that we talked about electrical systems, which involve three primary things: voltage, current, and resistance. And that was down here at the very bottom of these levels of abstraction. It involved physical electrons moving through a system. In this topic, we're actually going to move up a level to devices. So switches fall in the devices category. We're no longer concerned with exactly how electrons move through a particular system. So we've moved up a layer of abstraction, and we're working our way towards transistors, right? So again, we're working our way to these upper levels of abstraction, which is where the majority of the course is going to spend its time. So you'll remember in the last video that I brought up this idea of analog versus digital circuits, and you can see that those two things are kind of the next couple layers of abstraction above where we are now. I think it's actually a little bit important to talk about the difference between analog and digital circuits before we move on to switches themselves. So the difference between an analog circuit and a digital circuit is that in an analog circuit, the voltage can be literally an infinite number of values. So I can have any voltage at any point in time at any place within my particular circuit. Right, so in an analog circuit, the voltage is not restricted at all. It can be anything. In a digital circuit, which is where we're going to spend our time for this class, it's right in the name of the course, of course, those voltage levels are discrete. So that means there is a specific number of voltages that can exist within a system. And I think you would agree with me that that's an important abstraction to make, because it's much easier from the perspective of a computer or even a person to choose between a small number of set values versus a potentially infinite number of values. It's much easier to detect a small number of predetermined values versus values that could run across the entire spectrum. They could be literally anything. So in the realm of digital circuits, right, our voltages are going to be restricted to certain levels, which brings us to another important question, which is, if we accept the fact that we're going to use digital circuits, then why do we choose binary, right? Binary is a digital system that represents two voltage levels, right? Only two voltage levels. It's also a system of counting that we're going to see in later videos, right? So the fact that we only use two voltage levels changes how we think about numbers, changes how we think about logic. That's kind of the point of the course, to talk about the implications of that. But to consider why we only choose two voltage levels, consider, what's easier? If I give you 10 different things and ask you to distinguish between those 10 values, or if I give you two different things and ask you to distinguish between those two values? Right? It's much simpler, it's much easier, especially from the perspective of a circuit, of a computer, to detect between two different voltage levels than it would be to detect 10 different voltage levels. Especially when you consider the fact that the two voltage levels that we're going to be using here are basically on and off. So we're either going to have zero voltage or we're going to have some voltage, where in this case the typical voltage level is around 5 volts. It can be anywhere between 3 to 5 volts is a common level of voltage to represent on. Right? We'll talk about this more when we talk about transistors in the next video. But for now, please understand that we are going to be using the binary system because it reduces the amount of complexity in our system. It's much easier to create a circuit that can detect on versus off rather than 10 different voltage levels, even though from a human's perspective it might be easier to count in base 10, right? Another important consideration is noise. There's always going to be noise in a circuit. It's unavoidable. The term we use is cosmic rays that are floating around through the air. You can't see them, right? But they're there, and every once in a while those cosmic rays will come into your circuit and they'll knock some electrons out of place, and that causes behaviors in your circuit that you don't intend, that you don't plan for necessarily. And so the more circuit components you have, the larger the circuit you have, the more complex your circuit is, the more noise that system is going to have to deal with. That's just kind of the trade-off that you make there. So by keeping our system simple, by restricting ourselves to 2 voltage levels, we reduce the complexity of our circuits, and we reduce the amount of noise then that we have to deal with in our circuits as well. So with all of that information in mind, right, we accept that we're going to be on the binary system. Our voltage levels in this case are going to be 0, and somewhere between 3 to 5 volts is going to represent on. Right? That leads us to the topic of this video, which is switches. So a switch then is a very natural progression from talking about binary to talking about circuits, because a switch does what we just talked about. It represents something either being on or being off. So you see here, this is a schematic symbol for a switch. It's currently in the off position. You see it's not connected. If it were on, you'd see the line going all the way across. Right? And that's really all there is to it. It's either on and current can flow through, or it's off and current cannot flow through. You're probably already used to switches. Many of you, I'm sure almost all of you, have seen switches that look something like this. They're on almost every wall in every room that you've ever been in to turn the lights on and off, for example. And these switches are great. These switches are excellent for what we need them for, which is turning the lights on and off. But for the purposes of a circuit, for the purposes of digital logic, they're actually not the best tool for the job. And the reason for that is because they're very manual, right? If you want to turn the lights on, you have to physically get up, go over to the switch, and move it. You have to turn the switch on. And the same thing if you want to turn it off. So it's very manual. It can't be controlled automatically. Somebody has to physically move the switch. Consider if you had to do that in your computer. Your computer is basically lots and lots of different switches firing very, very quickly. What if you had to manually control all of those switches that were inside of your computer? You couldn't do it. It's just not possible for a human to even conceive of doing something like that. So we're not going to use these kinds of switches in this class. What we're going to use are transistors, which are a special kind of switch. And the nice advantage of transistors over the manual switches that we just talked about is that whether or not they are on or off is controlled by electricity. So it's controlled by voltage in this particular case. So we'll talk a lot more about transistors and how they work in the upcoming videos. But these are going to be switches, the switches that we're going to use in this particular class. Depending on what the voltage level is on the particular switch, current will flow through the transistor if it's on, or if it's off, then current will not flow through the particular transistor. So these transistors are relatively recent developments. They were invented back in the late 40s, early 50s. And their predecessor was something that was actually called a vacuum tube, which was a much worse version of a switch that was in use before the transistor came along. The transistor really revolutionized digital circuits and computing. And to think about why, some of the main advantages of these transistors are the fact that they're very small. Vacuum tubes used to be very, very large. There had to be a space for the vacuum to exist. They also were not very reliable. Vacuum tubes would break all the time, and they would have to be replaced very, very frequently. Transistors do fail sometimes, right? But they're much, much more reliable than vacuum tubes. And another, perhaps the most important thing with transistors is that they operate at lower voltage, which requires less power. This is good not just from an environmental standpoint, but also from the perspective of your electric bill. So when transistors came on the scene, that really was when the boom of digital computing started, and we're still riding that boom today. So in the next video, we'll talk a lot more about these transistors and how they actually operate, and then we'll start to piece them together into digital circuits.